Well, let's talk about daily temperature variations, specifically daytime warming. This particular graphic here, there's a lot of information going on here, but we have an x-axis, which is temperature in degrees Celsius or Fahrenheit, and then the altitude as we go from the Earth's surface on up. And as a point of reference here on the right-hand side, they show a meteorological weather instrumentation shelter. It's about 1.5 meters, or about 5.5 feet above the surface, is where the temperature is taken in a ventilated type enclosure. But what we want to look at here specifically is how temperature changes with height during the day with very little wind. Notice that, again, this is surface. We could list this as 0 meters up to about 1.5 meters here. And we see that temperature very near the surface, in this particular example, if we look at it in terms of degrees Celsius, is about 55 degrees Celsius. As we go up in altitude, what do you notice? Well, you notice temperature decreasing. Okay? And we would expect that with the incoming solar radiation heating the Earth's surface. And recall that the atmosphere is pretty much impervious to the incoming shortwave radiation, except for ozone. Ozone will absorb some of that incoming shortwave radiation. But on a cloudless day with very little winds, that's basically what we're looking at as far as a temperature profile. We see as we go up in altitude, temperature beginning to decrease. The temperature at this particular altitude is about 36 degrees Celsius. And as we go even further up, those temperature continues to flatten out a little bit. But our warmest temperatures will be near the surface, again, which is what we would expect with incoming solar radiation. And then temperature decreases rapidly as we head up into the atmosphere. Now, with windy conditions, however, the temperature profile will change a bit. Again, notice this particular line, temperature decreasing with height. This is the condition on a calm afternoon. But in a windy afternoon, we begin to have convection taking place. Recall, we talked about 3 methods of heat transfer in the atmosphere, one of those being convection, where we begin to get air rising because it's hotter, and then you begin to mix some of the air, take some of the cooler air here, mix down to the surface, take some of the warmer air at the surface and begin to mix it upward. What this ends up doing is flattening out the temperature profile here. Temperature is still decreasing with height, but not as rapidly. Let me clean this up a little bit here. Again, with windy conditions, we redistribute the temperature profile by mechanical convection. In other words, the wind is providing aid to transfer energy throughout the atmosphere. So instead of the temperature being up near 50 degrees Celsius on a windy day, we might see something around 40 degrees Celsius in this particular example. And then as we go up, temperature decreasing with height. If we go up to 2 meters, we see the temperature is at about 100 degrees Fahrenheit at about 2 meters, whereas down at the surface, the temperature is about 103 degrees Fahrenheit. So, this is one way that we can use energy transfer throughout the atmosphere, is through convection. Again, we talked about that back in Chapter 2. So a windy day actually helps to mix the atmosphere, in other words, to flatten out the temperature profile, as I mentioned before. Now, this particular graphic should look somewhat familiar. This particular part of the graph is temperature versus time of day. This is sunrise right here, sunset right here, and then basically what we have are 2 graphs in one. This particular bottom graph here that I'm outlining is the amount of energy coming in versus time down here on the x-axis. I'll clean this out so you can actually see it again. Let's take a look at, first of all, at the bottom graph here. Now, notice that we start here at midnight, and we go all the way through sunrise to noon to sunset, and then back to midnight. Now, the blue curve here is the long-wave radiation. This is the energy leaving the Earth. Recall that anything that has a temperature emits radiation at different wavelengths. So we have the amount of energy as we head toward sunrise. The Earth has been emitting energy all evening, and so as we begin to hit sunrise, we see this curve here beginning to take off. This curve here is the solar radiation coming in from the sun, and so our shortwave radiation increases to a maximum right around noon, and we're still receiving solar radiation from the sun all the way to about, in this example, to about 4 o'clock is where we have this positive energy. In other words, the energy coming in being the sunlight versus energy leaving the Earth, which is the long-wave radiation, we have a positive addition of energy into the system, which means we should see temperature increasing, which is what we do in this top graph. As long as the amount of short-wave radiation coming in exceeds long-wave radiation leaving, then we should see an increase in temperature. And this is what we see. And in fact, we see the maximum temperature occurring at about 4 o'clock. And this corresponds, let me clean this up here again just a bit. This maximum temperature here corresponds to the point where incoming radiation is equal to outgoing radiation. At this point, we're still receiving incoming solar radiation from the sun, but it's decreasing as we head towards sunset. And now you notice that we have more energy leaving the Earth, shortwave radiation indicated by the blue line, than we have coming into the system, which is shortwave. Long wave leaving the Earth, shortwave energy coming in. So now we have a deficit of energy, and we begin to see temperatures cooling. This is just what you saw in Budget Sim. Now you'll notice in the example I have here, we could look at this in terms of a bank account. The blue line here being money taken out of the bank, the brown line here being money put in the bank, and as long as we're putting more money in the bank than we're taking out, then we have positive cash flow here. However, if you get into a situation where you're taking out more out of your bank account than you're putting in, then you have a deficit, or you begin to bounce checks. Then you run into problems. So it's any type of budget. In this particular case, we're looking at the energy budget into the atmosphere. So that's the reason why maximum temperature typically occurs later in the day, because we're still receiving more incoming shortwave radiation than we're losing. Now, we're assuming that there are no significant cloud cover or passage of fronts. We also assume that there's not a large body of water nearby. In other words, in terms of a maximum temperature occurring later in the afternoon. As we're going to learn this semester, cold fronts, warm fronts, as we've already learned, cloud cover plays a role in keeping temperatures down during the day and keeping them up at night. And we also know that large bodies of water have a very high heat capacity. In other words, it takes a tremendous amount of energy input into an ocean or a body of water to raise the temperature by 1 degree Celsius. So you can think of large bodies of water as huge heat reservoirs. And so that impacts. You remember we were talking about partitioning of energy. Do we use that energy coming in from the sun for sensible heating, which would raise the temperature, or do we use it for evaporation, which would be latent heat? And that's what I've mentioned here, just the idea of energy partitioning. Also keep in mind the types of soil moisture content, and vegetation. Any of these can remove or can help to partition it off in terms of sensible and latent heat energy. Now, one thing I'd like to point out down here, notice that the region around 30 degrees north and south latitudes are examples of where most of the heat energy is being converted into sensible heating. We talked about this being areas where there are deserts, very little cloud cover, little or no moisture, little or no vegetation. So that's one of the reasons why we were talking about, although the sun is directly overhead at 23.5 degrees north and south latitude, depending upon the season that you're in, at 30 degrees north, there's really not a whole lot of partitioning of the energy. In other words, most of the energy is being used to heat the Earth's surface. And so that's the reason why we have 30 degrees north being some of the warmest areas. Let's take a look at nighttime cooling. Quite a bit different than what we see with daytime cooling. In fact, again, this particular graph here is altitude as we go from 0 meters up to, this is about 1.5 meters. Again, I'm using this weather shelter as a point of reference, sitting at the surface, and goes up to about 1.5 meters. You'll notice that temperature in this particular example is about negative 0.5 degrees Celsius at the surface. If we go up to about 1.5 meters, however, we see the temperature warming to 4 degrees Celsius. So now we have temperature increasing with height. Do you recall why this is happening? If you recall from radiation sim, we'll talk about that here in a moment, the atmosphere is a poor absorber and emitter of radiation in most cases. The ground itself is a very good emitter, depending upon soil content, depending upon moisture, vegetation, things like that. We'll come back and take a peek at that in a moment. But notice, temperature is increasing with height in the evening hours. And this is with very little wind. In other words, we don't have any type of mixing. So what are the physical mechanisms responsible for the nighttime cooling? Again, keep in mind this particular slide here where temperature is increasing with height. Let's talk about some of the physical mechanisms responsible. Well, we know that when we have more energy leaving the system, in other words, when we have infrared or long-wave radiation leaving the Earth, more leaving than incoming, we will see temperatures cooling. Also keep in mind that infrared radiation is being constantly absorbed and emitted by the Earth's surface 24 hours per day. In most cases, we typically lose more infrared energy than we gain, thus we cool. Now, at this point, we can define this type of profile where temperature is increasing with height. We call this radiational cooling. When the ground and the air directly above the ground are cooling because of the emission of long-wave radiation. In other words, it's losing energy. The average speed of the molecules begin to decrease, and recall that's how we define temperature, as the average speed of the molecules. So my question to you, which is the better radiator of infrared radiation? Is it the ground or the atmosphere? Let's take a look at the graphs below. Now this particular graph here is from RadSim, and this is over a freshly packed snow surface at night. And notice, right at the surface, again this y-axis being altitude in meters and temperature in Fahrenheit on the x-axis. Notice the temperature is increasing rapidly as we go from the surface and then begins to decrease once we reach this point up here. So what do you recall? Well, from this particular example, you would say that the ground is a much better emitter of infrared radiation. And we see this because the ground right near the surface is the coldest part. In other words, it's emitting most of its radiation. And the air directly above it, there's some transfer of energy there by conduction, but very little, since the atmosphere is a poor conductor in terms of thermal conduction. So, right after sunset, you see the Earth's surface is slightly cooler than the air directly above it. However, there is some transfer of energy, like I mentioned, by conduction. So we take some of the warmer air directly above the surface and we transfer it down to the surface, but the surface quickly radiates it away as infrared energy, and so it stays colder. At night, the ground and the air in contact cools more rapidly, like I said, because it continues to lose energy much more quickly than the atmosphere. We do have some transfer, like I said, from the warmer atmosphere to the ground, but this is a very slow process because of the problem with the air's thermal conductivity. We talked about that in Chapter 2. So now you have a pretty good idea of why temperature begins to increase with height at night. Now, just like during the daytime, we can have some forced convection, the winds. This particular temperature profile occurs during a windy evening. Notice we still have temperature increasing with height, but it's more of a gradual slope compared to this particular change in temperature with height on a calm night. So again, we take some of the, if we have windy conditions, we take some of the warmer air. If we were to look at this temperature profile here, we take some of the warmer air, transfer to the surface, some of the cooler air is brought up, and now your temperature profile begins to flatten out a bit. So a little bit warmer here compared to in the calm winds, but now a little bit cooler up here compared to what you would see on a calm night. Now, I've been talking about temperature increasing with height. There's an actual term for this. It's called a temperature inversion. And in fact, when that temperature inversion is caused by infrared radiation being emitted from the ground in terms of long wave energy, we term this radiation inversion. Okay, so temperature is increasing with height because the surface is losing its energy in terms of long wave radiation, and so it begins to cool. So what are some atmospheric conditions needed for radiation inversions? Well, we've already identified this, windless nights, or very light winds, because we don't want to promote mixing. In other words, warmer air from above being brought down to the surface and some of the cooler air from the surface brought above. If you want a strong radiation inversion, which is what this temperature profile looks like, strong increase of temperature with height. Notice the temperature changes here at about 29 degrees Fahrenheit at the surface, up to about 10 feet in the air. It goes to almost 38. There's almost a 10-degree change over 10 feet in a very calm night. Well, you need long nights. You know, we talk about radiation inversions occurring because the Earth is losing infrared radiation. The longer the night, the more infrared radiation the Earth can continue to lose, assuming that we have clear skies. Now, keep in mind, back in Chapter 2, we talked about clouds absorbing that radiation coming from the Earth and emitting their own infrared radiation back to the Earth, thus keeping temperatures up. So if you want a strong radiation inversion, in other words, a strong increase in temperatures with height at night based upon the Earth losing radiation, you need clear skies, dry air, snow covering the ground. Snow is an excellent emitter of infrared radiation, and so snow covering the ground. Loose soil. You know, you want to keep the heat that's in the ground, you want to keep it away from the surface, and the best way to do that is have loosely packed soil. You have air pockets in between the different soil particles, and we know that air is a poor thermal conductor. And so if you have that air space in the soil, it's not going to promote heat transfer from subsurface to the surface. And then, of course, a lack of vegetation, because vegetation can actually produce some problems with radiation inversions. At this time, what I'd like you to do is just take a few minutes to read a couple of pages there on thermal belts and protecting crops from the cold. I won't go into any detail here, but you will be responsible for exam questions from this particular area too. So just spend a few minutes, if you would, reading through that. Well, let's talk about controls of temperature. We've actually talked about some of these factors. We'll identify the main factors that cause variability in temperature. After all, you're going to be forecasting for temperature. And so we need to find out why temperature is different from place to place. Now, we've already talked about a temperature difference between the North Pole and Iowa. We talked about incoming radiation, at least at the top of the atmosphere, being greater over the North Pole than it is over Iowa at certain times of the year. But yet we're warmer, and we talked about the reasons behind that. We've already identified the greatest factor in determining temperature. That's the shortwave radiation coming in from the sun. but we'll also talk about other factors that influence temperature variability. First of all, the latitude that you're located at, the land and water distribution, ocean currents. Now, we haven't really talked so much about ocean currents yet. We will get into that in later chapters. But you may have heard of the Gulf Stream, which is a current of water that runs along the east coast of the U.S., typically warmer waters, which tend to influence land temperatures along the east coast of the U.S. Elevation, we'll also talk a little bit about that. Now, what you're looking at here is a map, longitude along the x-axis, latitude. You see the North American continent here. We'll look at that particular area as we look at this particular map. There's a lot of information here. And you're looking at temperatures. Now, these lines of temperatures, in other words, 70-degree temperature line runs all the way through here. And I'm going to give you a definition here. It's called isotherms. And an isotherm is a line of temperature. It's a contour of temperature. Everywhere on this 70-degree line indicates that temperature is 70 degrees. And you'll notice that as we go poleward, now this is average January temperatures. As we go poleward, temperatures begin to change, and they change rather rapidly. If you look down here along the Louisiana Gulf Coast area, we see temperatures, average temperatures in the 50s. We go up into Iowa, just a distance of about 1,000 miles. The average temperature jumps down to about 25. So we have a change of 25 degrees Fahrenheit over 1,000 miles. So temperatures change rapidly. There's also quite a few things here to notice. Notice that the temperature lines, the isotherms, are packed together much more closely over land than they are over the ocean. Temperatures do change over the ocean, but they change much more slowly. You have to go a larger distance. For instance, if we take a look at a latitude line here along the Gulf Coast, and we see an average temperature of 50. Well, if we go directly over to the coast, we see temperature here starts at 60. And to go to 0, you have to cover a larger distance going from 60 to 0 compared to doing the same thing over land. Let me see if I can clean this up just a bit. Again, going from, well, let's say we'll go 60 here to the 0 line. And going 60 to 0 over here. Notice this line is quite a bit longer than this line here. So temperatures change much more rapidly over the continent in January than they do over oceans. Any idea why? Well, you already have an idea. We talked about the ocean being a huge heat reservoir. In other words, it has to do with heat capacity, or specific heat in particular. And so the land cools and heats up much more quickly than the oceans. Also notice that the isotherms, that's the lines of constant temperature or equal temperatures, over the continent begin to point downward. Whereas over the ocean here, over the Pacific Ocean, they begin to point upward. Down over the ocean on this side, they begin to point downward. And notice right along the coast is a change where lines or the isotherms begin to spread out. Here they're tightly packed together, still tightly packed together, but as we go into the ocean, they begin to spread out. Same thing here, tightly packed together. Here they begin to spread out. So anywhere you have an ocean continent, and we can look over here, the same thing. Look over here. We have the temperature lines really bending out here, bending upward. So what's the cause for that? One other thing I'd like to point out as we're looking at this, notice that the isotherms, the lines of equal temperature, begin to oscillate up and down. But here, over the southern hemisphere, you can pretty much draw a straight line. What's the reason for that? We have a little bit of bend there, but we have a lot of bending in the northern hemisphere of the isotherms compared to the southern hemisphere. We've already hinted at that. That has something to do with the distribution of land and ocean. There's much more water in the southern hemisphere than there is in the northern hemisphere. We talked about heat capacity, and so there's not a large change in temperatures with large bodies of ocean. Well, let's take a look at the average July temperature. Now, notice over the North American continent here. Obviously, temperatures are warmer. And, however, there aren't as many isotherms present. Okay, let's back up here a second. I'll clean this up here. Notice quite a few isotherms here. In other words, temperature changing rapidly as we go from north to south. However, here, looks like temperatures here in the south are in the mid-80s. We go up into Iowa and we see average temperatures here in the mid-70s. So there's only about a 10-degree temperature difference in terms of average temperatures per 1,000 miles as we go from Iowa to the Gulf Coast. Whereas in the wintertime, there was a 25-degree change over 1,000 miles from the Gulf Coast to Iowa. So the isotherms aren't as packed over the land masses. Also notice that if we look over the ocean, that the isotherms begin to bend down here. They begin to bend up here. We'll talk about why that occurs here in a little bit. Again, if we look at the southern hemisphere, pretty much straight across. Not a whole lot of change in terms of the packing of isotherms. Do you notice this area right here? Notice it has a bullseye of 70-degree temperatures. What do you think the reason for that is? Well, that has to do with elevation. That's an effect of temperature. This is where the Himalayan mountains are located at. And so we're seeing the effects of elevation there. Also notice this area of 90 to 100 degree temperatures. Also notice a 90-degree temperature here. Now notice that this is in an area near 30 degrees north latitude. You recall we talked about that being an area of very little cloud cover, very little vegetation, very little moisture. And so what we see along this particular area is most of the energy coming in from the sun being used for sensible heating. Now if we go back to the average January temperatures and we look at the southern hemisphere, notice we have 90-degree temperatures here. Over here, over this continent here, that's Australia. And notice where that's located, at about 30 degrees south latitude. So, some observations are to summarize in terms of the controls of temperatures. Temperatures typically decrease as you head poleward. We have a tighter packing of isotherms in January compared to July, and we'll learn why that occurs here in a few lectures later. Notice also the bending of isotherms near ocean-land interfaces. That has something to do with the heat capacity of land compared to oceans. And then I chose a line of latitude and I compared continental temperatures versus oceanic temperatures at the same latitude. Some of the things that we notice, the isotherms bending up or down on both coasts during the summer months, and we ask why. We'll talk about that in just a little while. What I'd like you to do at this point, we have some information on air temperature data that I'm not going to cover at this point. I'm going to ask you to read pages 72 through 74 for terminology. Some of the terminology is how they come up with average temperatures. One term that I will define from this particular set is what we call the daily diurnal range of temperature. diurnal being the key word here. This is defined as the difference between the maximum temperature and minimum. In other words, the range. The daily high, the daily minimum, we call that the diurnal, which means as we go from day to night, change of temperatures. We'll look at some of the characteristics of diurnal temperature and some actual practical applications of using the temperature data. First of all, before we actually look at some of the practical applications, let's talk about characteristics of diurnal range of temperatures. Typically, the largest diurnal range is at the Earth's surface, typically larger on clear days. Largest range, or the largest range of temperatures, occurs on high deserts. Typically, the diurnal range is smaller in humid regions. Part of that has to do with the fact that the incoming energy is being partitioned off into sensible and latent heat of evaporation, and so not all of it's being used for sensible heating. Typically, the diurnal range is smaller at coastal cities. In other words, if you were to look at the average temperature, let's say in Mobile, Alabama, along the Gulf Coast, the difference in the maximum temperature and the minimum temperature in the summer is not going to be very much compared to here in Iowa. For instance, Mobile may hit a high of about 85 and a low of about 75, so there's only a 10-degree difference. In other words, that range difference in temperature is about 10 degrees. You look at Iowa, we might see a high of 90 and a low of about 65 or 70. And so we're talking about a 20 to 25 degree difference at the same time. And so obviously the humid regions, the change in temperature is not as great. Smaller coastal cities, smaller in the concrete jungle. You look at urban heat islands, that's a term. Basically where you have a lot of concrete. If you look at Des Moines, Iowa, one of the things I would ask you to pay attention to when you're watching the nightly weather forecast is look to see what the minimum temperature is in Des Moines compared to, let's say, Ames. Typically, Ames is going to be a few degrees cooler. Or if you look into southern Iowa, they may be a few degrees cooler where you don't have so much concrete. You should be prepared to discuss all the physical mechanisms responsible for the above diurnal range characteristics. And we've talked about these, and I've mentioned a few of these here. Let's take a look at some of the practical applications of temperature data. We'll look at these in terms of what we call heating degree days, cooling degree days, and growing degree days. Heating degree days, this is based on the assumption that people will start using their furnaces once the mean daily temperature drops below 65 degrees Fahrenheit. Recall that the mean daily temperature is defined as the max and min temperatures averaged together. And so the formula for this is the 65 degrees Fahrenheit minus the mean daily temperature. So for instance, let's say that the mean daily temperature for today was 55. We would take the formula 65 minus the 55 degrees Fahrenheit, and we would accumulate 10 heating degree day units. However, if the mean daily temperature is greater than 65, then there are no heating degree days. What you're looking at here is an average of heating degree days during the winter time. You'll notice along the Gulf Coast, not a whole lot of heating degree days. As we progress further north where it gets colder, as you would expect, the heating degree days would increase. And so as you go from south to north, heating degree days begin to increase. Next item we'll look at are cooling degree days, and this is just based on the assumption that people will begin to use their air conditioners when the mean daily temperature rises above 65 degrees Fahrenheit. So this is for the warm months of the year. The formula is the mean daily temperature minus 65 degrees Fahrenheit. So for instance, let's say that we have a high temperature of 90 and a low temperature of 70. Our mean daily temperature would be 80 degrees minus 65, and that would give us 15 cooling degree days. Again, if the mean temperature is below 65, then there are no cooling degree days. So basically, The use of heating degree days or cooling degree days are made decision-making processes for such industries as power, gas companies, construction companies. For instance, power companies during the summer will expect an increase in energy usage once we get above 65 degrees, whereas during the wintertime, oil companies, gas companies will expect more use of furnace as we go through the wintertime. What you're looking at here are cooling degree days. Again, we're talking about during the summer, and as you would guess, cooling degree days are higher in the south than they are up in our neck of the woods. Now, growing degree days is something that probably many of you are familiar with. This is an index typically used by farmers as a guide for planting and harvesting. There are multiple ways of calculating growing degree days, but the most common one, especially used here in Iowa, are what we call using the mean daily temperature. We use this because the main factor in terms of physiological development of plants is temperature and moisture to a certain degree, but temperature is a good indicator. The formula for heating degree days is the mean daily temperature minus 50 degrees Fahrenheit for corn. Now, depending upon the type of crop that you're planting and harvesting will determine what your base temperature is. And there is a table here, table 3.2 in your textbook, that lists the base temperatures for crops such as beans, corn, cotton, peas, rice, and wheat. Notice those of you from Indiana, any of you have any relatives in Indiana, the base temperature for wheat is 40 degrees. Sweet corn itself can be harvested when you accumulate 2200 degree days, growing degree days. One caveat, though, with this is if the mean daily temperature is above 86 Fahrenheit, the crop will become stressed and thus inhibiting the maturation process of the corn. So let's just take a typical July day. Our average temperature might be 80. And if we're looking at corn, we subtract 50. And that's 30 growing degree days for that particular day. And so this is a good practical use here in the Midwest for growing degree days. What I'd like you to do is to close out the material from pages 77 through 81. I'd like you to read through that. You will be responsible for identifying the different types of thermometers that are used in there and briefly describe how they function. Nothing in detail, but just a brief description of how they function are the things that you'll be held responsible for. Well, this is the end of Chapter 3. I hope you've learned quite a bit, and have a good day.